Hey everyone! Ever wondered how your DMs stay private? Or what that little lock icon in your browser is actually doing? Well, you've come to the right place. In this explainer, we're going to totally demystify encryption. We're breaking down the must-know concepts, making them super simple and, easy to remember, especially if you've got an exam coming up. Ready? Let's do this.
Okay, so let me ask you something. Think about everything you do online. Your emails, your texts, all that late-night browsing. Is it all just out there, like an open postcard for anyone to read? Or is it sealed up tight, inside a locked box that only the right person can open? Seriously, that one simple difference, that's the whole point of encryption.
All right, here's our game plan. First up, we'll tackle the postcard problem, the big why. Then, we'll get into the 2 magic tricks behind every code. We'll even hit up ancient Rome for a bit before jumping into how computers do it today. And finally, we'll cover the rulebook and the whole cat and mouse game of code breaking. It's going to be good.
Okay, let's kick things off with Section 1, the postcard problem. This is all about why we even need to protect our digital secrets in the first place.
This slide really nails it. Look at the top half. That's your data, unencrypted. It's basically a postcard. As it zips across the internet, any server, any router that touches it can read your whole message. Just plain as day. But now look at the bottom. That's the locked box. The message is sealed up tight. Sure, the internet can see the box and where it's headed, but they have absolutely no clue what's inside. Only the person with the key can unlock it. Huge difference, right?
And that brings us to such a critical idea. Get this, encryption doesn't actually stop someone from grabbing your data. No way. What it does is make that data completely meaningless to them. So yeah, they might have the locked box, but without the key, it's just a box of gibberish. It's all about protecting the meaning, not stopping someone from getting their hands on the scrambled mess. So the big question is, how do we actually make that locked box? Well, that's what Section 2 is all about. Encryption's 2 magic tricks. And trust me, it sounds way more complicated than it is. Almost every code you can think of, from ancient stuff to what your phone uses, is built on just 2 simple building blocks.
Okay, magic trick number 1 is called substitution, and it's exactly what it sounds like. You just replace stuff. Think of it like a secret recipe where you swap ingredients. Instead of flour, your secret codebook says to use sand. So here, for every letter in hello, we swap in something else, and we get this random-looking QXZ11. Simple, right? You're just swapping one thing for another. And trick number 2 is permutation. That's just a fancy word for shuffling. So going back to our secret recipe, this is like taking all the steps, mix flour and sugar, add eggs, and just shuffling the order. You have all the same letters, but you mix them up. So hello becomes low hell. See? All the same pieces, just in a totally different order. And modern encryption, it just does both of these things, substitution and permutation over and over and over.
So at the end of the day, what's the goal here? It's all about hiding patterns. You're taking something that makes sense, we call that plain text, and turning it into something that looks like total gibberish. We call that ciphertext. But, and this is the golden rule, you absolutely have to be able to reverse it. With the right key, you need to get that original message back perfectly. Remember, encryption hides information, it never ever destroys it.
Okay, let's jump to Section 3, Ancient Codes, Perfect Secrets. We're going to look at a super simple old-school code and compare it to one that's, believe it or not, perfectly unbreakable.
All right, first up, the classic Caesar Cipher. Seriously, just think of one of those decoder rings you got from a cereal box. All you do is agree on a secret number with your friend. That's the key. Let's say you pick 3. So to encrypt H, you just shift it forward 3 spots in the alphabet. I, J, K. So H becomes K. You do that for the whole word, and boom, hello becomes KHOOR. It's pure, simple substitution. So why is this so bad? Well, for one, there are only 25 possible keys. You could just try them all and crack it in like a minute. But the real fatal flaw is that it doesn't hide the patterns of the language. For example, we all know E is the most common letter in English, right? So a codebreaker just looks at the scrambled message, KHOOR, finds the most common letter, in this case O, and guesses, hey, that's probably E. And once they have that, the whole thing just falls apart.
Okay, now let's swing to the total opposite end of the spectrum, the one-time pad. This thing is theoretically perfect. It's impossible to break.
Imagine you and your friend have two identical magic books filled with random characters. To send a message, you use page 1 of the book as your key, encrypt your message, and then you both burn that page. You never use it again. Because the key is totally random and you only use it once, the scrambled message is also totally random. It's mathematically unbeatable. So, what's the catch? Well, imagine trying to securely deliver a new key that's the size of a Netflix movie for every single movie you want to watch. Yeah, not gonna happen. It's just not practical for the real world.
Okay, so how did we go from shifting letters around to the kind of encryption our phones use? That brings us to Section 4, how computers encrypt today.
The real game changer was when we stopped trying to encrypt letters and started encrypting what computers actually see, bits. Your computer has no idea what the letter A is. To a computer, it's just a bunch of zeros and ones. Think of it like a panel of light switches. Using a standard called ASCII, the letter A becomes the number 65, which is just this specific pattern of on and off switches. And that binary code is the raw ingredient for all modern encryption.
So, encrypting one tiny bit at a time would be super slow, right? So instead, modern systems use something called a block cipher. It's pretty clever. It just takes all that data, all those ones and zeros, and chops it up in a nice, neat, fixed-size chunks we call blocks. Then, the algorithm gets to work on one full block at a time, scrambling everything inside it.
And what's the gold standard for this today? It's something called AES, the Advanced Encryption Standard. And the block size it uses? 128 bits. That's the magic number. Every single chunk of data it scrambles is a string of 128 ones and zeros. Okay, so that leads to a pretty obvious question, right? If AES only works on these tiny 128-bit chunks, how in the world do we encrypt, like, a whole movie file? Well, that's where the rulebook comes in. Let's get into Section 5, the rulebook for encryption. Okay, listen up, because this is probably the most important mistake to understand. The easiest way to handle all those blocks is something called electronic codebook mode, or ECB. But it has a massive, fatal flaw. If you have two blocks of data that are exactly the same, ECB will encrypt them into two new blocks that are also exactly the same. And that leaks patterns. Look at this picture. Even though it's technically encrypted, you can still totally see the outline, right? That's because all the identical white blocks became one thing, and all the identical black blocks became another. It's a huge security hole.
Okay, so this table right here, this is basically your cheat sheet for your exam. We already know ECB is bad. It leaks patterns. So how do we fix it? Well, look at CBC, or cipher block chaining. It's smart. Before it encrypts a block, it mixes it with the scrambled result of the last block. So even if you have two identical blocks of plain text, they'll end up looking totally different. Then there's CTR, or counter mode. This one's also really cool. It basically encrypts a unique number for each block and uses that to scramble the data. The big win here? You can encrypt all the blocks at the same time, which makes it super fast.
And all this talk about good modes and bad modes leads us perfectly into our final section, the ongoing arms race between breaking codes and building them stronger.
Yeah, this whole science of analyzing and breaking codes is called cryptanalysis. And it's really important to remember that these folks aren't the bad guys. A much better way to think of them is as ethical locksmiths. Their job is to test our digital locks, find all the weaknesses, and then report back so we can build stronger ones for everybody. It's that constant testing that makes our encryption better over time. Okay, let's wrap this up with the key takeaways for your exam. Here we go. Number 1, encryption protects meaning, not access. 2, the magic tricks are substitution and permutation. 3, the modern standard is AES with 128-bit blocks. 4, and this is the big one, avoid ECB mode because it leaks patterns. 5, use secure modes like CBC or the super efficient CTR. And finally, 6, cryptanalysis is what pushes everything forward and keeps us safe. Got it?
So we'll leave you with this one last thing to chew on. The blueprints for our best locks, like AES, they're totally public. Anybody can go look up how they work. The security isn't in the lock design, it's in keeping your key secret. So, if everyone knows how the lock is built, what's the next big battleground for keeping our digital lives private? Something to think about.